All right, welcome back, everyone. For today's deep dive, we're going to be looking at some really cool recent research in mathematics.
Oh, very cool.
Specifically, we're going to be exploring the world of graph theory.
Okay.
And focusing on this fascinating concept called Ollivier-Ricci curvature.
Yeah.
You sent in a dense research paper.
It is dense.
Titled A Relation Between Isoperimetry and Total Variation Decay with Applications to Graphs of Non-Negative Ollivier-Ricci Curvature. And wow, it's packed with some seriously interesting stuff.
Yeah, this paper, it really delves into the deep connections between the geometry of graphs and the behavior of random walks on those graphs.
And I know you're no stranger to these concepts.
No, not at all.
So we're just going to jump right in.
Okay, sounds good.
For starters, can you give us a quick rundown of what isoperimetric profiles and total variation decay are all about?
Sure. So in essence, the isoperimetric profile of a graph provides a way to quantify its shape by examining the relationship between the size of a set of vertices and the size of its boundary.
Oh.
It tells us essentially how much surface area a given volume of the graph has.
So a graph with a small isoperimetric profile would have sets of vertices that are kind of tightly packed together.
Exactly.
Like a sphere in geometry.
A sphere is a classic example of a shape with a small isoperimetric profile.
Okay.
Now, total variation decay, on the other hand,
Yeah.
that relates to the behavior of a random walk on a graph.
Right.
It measures how quickly the probability distribution of the random walk's position spreads out over time.
Okay.
The faster the decay, the more rapidly the random walk explores the graph.
So in a way, the isoperimetric profile is about the static shape of the graph, while total variation decay is about the dynamic movement on that graph.
That's a great way to put it.
Okay.
And what this paper does is establish a beautiful connection between these two seemingly disparate concepts.
That's what I love about math. Always finding these unexpected connections.
Right.
It's beautiful.
So the core result of the paper is this inequality that links the graph's isoperimetric profile to the decay of its random walk's total variation distance.
Exactly.
Can you walk us through that?
Absolutely. The inequality essentially states that if the total variation distance decays rapidly, then the graph must have a large isoperimetric profile.
Okay.
In other words, if the random walk spreads out quickly, then the graph must have sets of vertices that are relatively spread out as well.
That makes intuitive sense.
Yes.
If it's easy for the random walk to explore the graph itself can't be too bunched up.
Right.
What's particularly interesting is that this result has major implications for graphs with non-negative Ollivier-Ricci curvature.
It does.
Can you remind us what that means?
Sure. Ollivier-Ricci curvature is a concept that's analogous to curvature in Riemannian geometry.
Right.
But applied to discrete spaces like graphs.
A graph with non-negative Ollivier-Ricci curvature, roughly speaking, means that nearby points tend to spread apart as you move along the graph.
Okay.
It's a way to quantify the expansion of the graph.
So this paper is telling us that for these expanding graphs, the random walk can't explore too efficiently.
Precisely. And that leads to a pretty surprising result.
Oh.
Bounded degree graphs with non-negative Ollivier-Ricci curvature cannot be expanders.
Hold on. Can you remind us what an expander graph is again?
Certainly. Expander graphs are networks that are incredibly well connected. Despite having relatively few edges, think of them as communication networks where information can travel very efficiently between any 2 points.
Got it. So these graphs with non-negative curvature, they can't be these super efficient networks. That seems counterintuitive.
It does, but the math shows us that there's a fundamental tension between non-negative curvature and the properties of expander graphs. This paper provides a quantitative way to prove this, and that's where Theorem 1.1 comes in.
All right, let's dig into Theorem 1.1.
Okay.
This seems to be the heart of the paper.
It is.
Can you explain what it states?
Essentially, Theorem 1.1 provides a way to construct sets of vertices with small boundary to volume ratios based on the total variation decay of the random walk.
Okay.
The smaller the ratio, the more compact the set.
So if the random walk spreads out slowly, indicating slow total variation decay.
Yes.
This theorem guarantees the existence of these these compact sets of vertices.
Exactly. It gives us a concrete way to link the behavior of the random walk to the geometric structure of the graph.
To make this more concrete, let's look at some examples from the paper.
Yeah.
First up, the integer lattice,
Yes.
denoted as z.
Uh-huh.
Can you remind us what that is and how this theorem applies in this case?
Sure. The integer lattice is simply the set of all points in d-dimensional space with integer coordinates. Imagine a grid extending infinitely in all directions.
Okay.
That's essentially what a lattice is.
Okay, so how does Theorem 1.1 work with this grid?
Well, in this case, the total variation decay of the random walk is known to be relatively slow.
Okay.
And as the theorem predicts, we can indeed find sets of vertices in the lattice that have small boundary to volume ratios.
Okay.
Think of a large cube within the lattice.
Yeah.
It has a relatively small boundary compared to its volume.
Right. So the theorem holds true for this classic example.
Yes.
Now, the paper also discusses a less familiar example, the lamplighter group.
Okay.
Z2AZ.
Right.
Could you explain what a lamplighter group is?
Yeah.
For those of us who might not be familiar with the term?
Yeah, imagine an infinite street with streetlights at each integer point.
Okay.
And a lamplighter walks along the street, turning lights on or off,
Okay.
according to a certain rule.
Mm.
This forms the basis of the lamplighter group, which has a more abstract mathematical structure.
Wow, that's a very visual way to describe it.
Yeah.
So how does this lamplighter group example relate to the theorem?
Well, the lamplighter group has a specific structure that leads to a particular rate of total variation decay.
Okay.
And when we apply Theorem 1.1 to this group,
Uh-huh.
the bounds it provides are remarkably close to the actual values we can calculate.
So it demonstrates the near optimality of the theorem.
Precisely. It shows that the theorem isn't just some abstract mathematical result.
Right.
It provides tight and accurate estimates in concrete examples.
That's pretty impressive.
Yeah.
Now let's talk about the proof of Theorem 1.1.
Okay.
I know our listeners are eager to hear the details.
I bet they are.
Can you give us an overview of the proof strategy?
Of course. The proof relies on a powerful concept called simultaneous near-optimal coupling of random walks,
Okay.
which is detailed in Theorem 3.1 of the paper. This technique allows us to analyze multiple random walks, starting from different vertices, in a way that reveals crucial information about the graph's structure.
Okay, so this coupling links the random walks together in some way.
Exactly. Imagine you have multiple random walks starting from different points on the graph.
Okay.
This coupling allows you to link these walks together in such a way that they tend to stay close to each other.
Mm.
They're not moving independently.
Yeah.
They're coupled together.
So it's like having a bunch of particles undergoing random motion.
Yeah.
But they're all attached to each other by invisible strings.
Yeah.
Preventing them from drifting too far apart.
That's a very good analogy.
Okay.
And what makes it near optimal is that the probability of these coupled walks diverging is very small.
Okay.
This property is crucial for the proof.
I see. By carefully constructing this coupling,
Yes.
we gain insights into the structure of the graph itself.
Precisely. These coupled walks, in a sense, act as representatives that capture the overall behavior of random walks, starting from any vertex on the graph.
And these representative walks guide us in partitioning the graph's vertices in a way that reveals these sets with small boundary to volume ratios.
Exactly. The idea is to group together vertices based on which representative walk they're most closely associated with.
Oh, yeah.
This grouping then reveals the sets we're interested in.
Fascinating. So this coupling acts like a guide,
Yeah, think of it like that.
leading us to the sets that have these desirable isoperimetric properties. Can you elaborate a bit more on how this grouping works?
Well, the paper formalizes this grouping process using the concept of a random equivalence relation.
Okay.
It basically defines a rule for deciding whether two vertices belong to the same group
Right.
or equivalence class,
Yeah.
based on the behavior of the coupled random walks.
So it's like saying if two vertices are likely to be visited by the same representative random walk, then they belong to the same equivalence class.
That's a great way to think about it. And these equivalence classes, defined by this relation, are precisely the sets we are interested in, the sets with small boundary to volume ratios.
Okay.
But there is a lot more to unravel about the intricacies of this equivalence relation and its implications.
Okay.
And we'll delve into those details in part 2 of our deep dive.
This is already blowing my mind. I can't wait to dive deeper in part 2. See you all there.
See you there. Welcome back to our deep dive into the fascinating world of isoperimetry and total variation decay.
Yeah, this is great stuff.
When we left off, we were just starting to unravel the intricacies of this random equivalence relation
Right.
and how it helps us identify these special sets with small boundary to volume ratios.
Right. I'm still trying to wrap my head around how these coupled random walks lead us to these particular sets.
Right.
Can you walk us through the logic a bit more?
Absolutely. So let's delve a bit deeper into how this equivalence relation actually partitions the vertices of the graph. Recall that we have these representative random walks that we've carefully coupled together.
Right.
Now, the equivalence relation essentially says that two vertices belong to the same equivalence class if and only if their corresponding representative walks have a high probability of meeting within a certain time frame.
Okay, so if the coupled walks starting from those two vertices are likely to collide,
Yeah.
then those vertices are grouped together.
Exactly. And this grouping is based on the underlying geometry of the graph.
Okay.
Vertices that are close in the sense of the graph structure are more likely to have their representative walks meet quickly.
That makes sense. So we're essentially using these coupled random walks to probe the underlying geometry of the graph
Yes.
and cluster vertices based on their proximity.
Precisely. Now, the key insight here
Yeah.
is that these equivalence classes formed by this grouping process tend to have small boundary to volume ratios.
Ah, so that's how we finally get to those special sets. But why is that the case? Why do these equivalence classes tend to have this property?
It's a consequence of how we've defined the equivalence relation and the properties of the near-optimal coupling.
Okay.
Remember, the coupled walks are designed to stay close to each other with high probability.
Right.
This means that vertices within the same equivalence class,
Yeah.
whose walks are likely to meet,
Uh-huh.
are also likely to be surrounded by other vertices from the same class.
So there's a sort of clustering effect happening within each equivalence class.
Exactly. And this clustering effect is what leads to the small boundary to volume ratios.
Okay.
Because the vertices within a class are tightly grouped together.
Right.
They have relatively few connections to vertices outside their class, hence a small boundary.
I see. So by carefully constructing this equivalence relation based on these coupled random walks,
Right.
we're essentially revealing the inherent clusters within the graph that exhibit these desirable isoperimetric properties.
Precisely. It's like we're using the random walks to color the vertices of the graph. Oh, okay.
And the colors reveal these hidden clusters with small boundary to volume ratios. But of course, this is just an intuitive explanation.
Sure.
The paper provides a rigorous mathematical proof of this connection.
Right. And I know our listeners are itching to hear about that proof. Can you give us a taste of how it works?
Of course. The proof hinges on showing that at least one of these equivalence classes has a boundary to volume ratio on the order of a specific quantity, ta,
Okay.
with positive probability.
Yeah, okay.
This quantity, ta, is a measure of the total variation decay of the random walk.
So if we can find even just one equivalence class with this property, it proves the theorem.
Exactly. It's like finding a needle in a haystack. We don't need to find all the needles, just one.
Right.
And to find this needle, the paper utilizes a clever argument based on lemma 3.3.
Ah, lemma 3.3.
Yes.
That seems to be a key piece of the puzzle. What does this lemma tell us?
Lemma 3.3 provides a way to bound the expected boundary to volume ratio of a randomly chosen equivalence class.
Okay. It essentially says that this expected ratio cannot be too much larger than team.
So it connects the geometry of the sets,
Yes.
their boundary to volume ratios, to the behavior of the random walk.
Right.
It's total variation decay.
Exactly. And this connection is crucial
Okay.
by carefully choosing a suitable value for inteen
Right.
and combining this lemma with the properties of the random equivalence relation.
Okay.
We can guarantee the existence of at least one equivalence class with the desired small boundary to volume ratio.
That's really neat. So by combining this bound on the expected ratio with a clever choice of parameters,
Yes.
we can ensure that at least one of those equivalence classes hits that target ratio.
Precisely. And that completes the proof of Theorem 1.1.
Wow.
It's a beautifully elegant argument that weaves together probabilistic and geometric concepts.
I'm really impressed by how the authors brought all these pieces together.
Me too.
Now, the paper also mentions some addition concepts like the massive green metric.
And the mass transport principle. Can you tell us a bit about those and how they relate to this work?
Certainly. The massive green metric is a way to measure distances on a graph based on the probabilities of random walks.
Okay.
Imagine you have a network of roads.
Okay.
And you want to measure the distance between 2 points, not by their physical separation,
Right.
but by how long it takes a random driver to travel between them. That's analogous to the massive green metric.
Okay.
It turns out that this metric is closely related to the random walk's information content.
Okay.
How much information about its starting point is revealed by its current position.
So instead of measuring distances with a ruler, we're measuring them with probabilities and time. That's a wild concept.
It is, and what's fascinating is that the upper tail estimates for the random walk's displacement and information content, which we discussed briefly in part 1, can be applied to this massive green metric. This provides a deeper understanding of how the random walk's behavior is constrained by the underlying geometry of the graph.
So these seemingly abstract concepts of random walks and information content are actually deeply tied to the geometric structure of the graph, as measured by this massive green metric.
Exactly. It's a beautiful illustration of how seemingly disparate concepts in mathematics can often be connected in surprising and profound ways.
Now you also mentioned the mass transport principle.
Yes.
What's that all about?
The mass transport principle is a powerful tool used to analyze properties of graphs and networks.
Okay.
By considering the flow of mass within the network,
Okay.
it's often used to derive global properties of the graph from local information.
Can you give us an example?
Imagine you have a network of pipes, and you want to understand how fluid flows through this network. The mass transport principle provides a way to track the movement of this fluid and derive global properties of the network, like its overall capacity or flow rate, from local information about how the fluid moves through individual pipes.
So it's like having a way to see the big picture by zooming in on the small details.
Exactly. And in the context of this paper, the mass transport principle is used implicitly in the proof of lemma 3.3.
Okay.
The lemma that provides the bound on the expected boundary to volume ratio.
Right.
It allows us to relate the global property of the graph, the existence of sets with small boundary to volume ratios, to the local behavior of the random walk.
Wow. It's amazing how all these different concepts from probability, geometry, and even fluid dynamics come together in this research.
It truly is a testament to the interconnectedness of mathematics and the power of these tools to reveal hidden patterns and relationships. And we've only just scratched the surface. In part 3, we'll delve into the broader implications of these findings and explore the potential applications of this research in various fields.
Okay, can't wait.
Stay tuned.
Welcome back to the final part of our deep dive into isoperimetry and total variation decay. We've been on quite a journey through the world of graph theory, random walks, couplings, and equivalence relations. It's amazing how all these seemingly abstract mathematical concepts can have real-world applications.
Absolutely. That's the beauty of mathematics, its ability to uncover hidden connections and provide insights into the structure and behavior of complex systems.
So let's talk about those connections. What are some of the potential implications of this research? Where could these findings be applied?
Well, one area where this research could have a significant impact is in the analysis of real-world networks. Think about social networks, transportation systems, the internet. They can all be represented as graphs.
Right, and by understanding the isoperimetric properties of these graphs, we can gain insights into their efficiency, robustness, and overall structure. But how exactly does that work?
Let's take the example of a transportation network, say a network of roads connecting different cities. The isoperimetric profile of this network can tell us how well connected the cities are and how easily traffic can flow between them.
So a network with a small isoperimetric profile would mean that cities are tightly clustered together and well connected, allowing for efficient transportation.
Exactly. And a network with a large isoperimetric profile might indicate bottlenecks or areas where transportation is less efficient due to the spreading out of cities and fewer connections.
That makes sense. So by analyzing the isoperimetric profile, we could potentially identify areas for improvement in the network's design or even predict traffic patterns.
Precisely. And this principle applies to other types of networks as well. For example, in a social network, the isoperimetric profile can provide insights into how quickly information spreads or how easily communities can form.
So this research could have applications in fields like urban planning, social sciences, and even marketing.
Absolutely. The tools and techniques developed in this research could be used to design more efficient transportation systems, understand the dynamics of social groups, or even target advertising campaigns more effectively.
Now, the paper also touches upon the open question of whether non-negatively curved bounded degree graphs of superpolynomial growth even exist. Can you remind us what that means and why it's such a big deal?
Certainly. Remember that non-negative curvature in a graph implies a certain kind of expansion property. Superpolynomial growth means that the number of vertices in the graph grows faster than any polynomial function of the distance from a fixed point. Finding a graph that satisfies both of these conditions would be a significant discovery.
So we're talking about networks that expand rapidly while still maintaining this non-negative curvature property.
Exactly. And the question of whether such graphs exist has puzzled mathematicians for some time. If they do exist, it would challenge our current understanding of the limitations imposed by non-negative curvature. It would mean that even with this curvature constraint, networks can still grow at an astonishing rate.
And if they don't exist?
Then it would establish a fundamental limit on the growth of networks with non-negative curvature. It would mean that this curvature condition places a strong constraint on the large-scale structure of networks.
Either way, it seems like an important question with the potential to reshape our understanding of graph theory and its applications. Now, before we wrap up this deep dive, I have one final question that's been lingering in my mind. The paper focuses on graphs, which are discrete objects. But could these methods be extended to study other geometric properties of graphs, or even to explore continuous spaces?
That's a great question, and it points to a very active area of research. Many mathematicians are working on extending the concepts of curvature and isoperimetry, from the discrete world of graphs to the continuous realm of manifolds and metric spaces. The idea is to develop analogous tools and techniques that can be applied to these more general geometric settings.
So it's like taking the insights we've gained from studying networks and using them to understand the geometry of more complex spaces like curved surfaces or even the fabric of space-time itself.
Precisely. The techniques and ideas developed in this research could potentially provide new tools for studying problems in differential geometry, topology, and even physics. It's a testament to the power of mathematics to bridge the gap between seemingly disparate fields and to provide a unified framework for understanding the structure of our universe.
Well, on that note, I think we've reached the end of our deep dive. It's been an incredible journey through the fascinating world of isoperimetry, total variation decay, and the surprising connections between probability geometry and the behavior of complex systems.
It's been a pleasure to explore these ideas with you. The beauty and power of mathematics lie in its ability to uncover hidden patterns and to provide profound insights into the nature of our world.
And to our listeners, thank you for joining us on this intellectual adventure. We hope you've gained a deeper appreciation for the elegance and significance of this groundbreaking research and for the boundless potential of mathematical exploration. Keep exploring, keep questioning, and keep pushing the boundaries of knowledge. Welcome back for another deep dive. Today we'll be tackling a paper with a pretty hefty title.
Oh, yeah.
A relation between isoperimetry and total variation decay with applications to graphs of non-negative Ollivier-Ricci curvature.
Definitely a mouthful.
It is, but the paper itself is really interesting, particularly when it comes to graphs with non-negative curvature. I know you're already pretty familiar with this area,
Yes.
but I think this paper offers some really interesting new insights.
Yeah, what I find really fascinating is how this paper connects these two seemingly disparate concepts,
Right.
The isoperimetric profile, which kind of captures the robustness of a graph, and then the total variation profile, which measures how quickly information spreads through a random walk.
Yeah. It's almost like you're looking at the shape of a network versus, how quickly gossip would travel through it.
Yeah, exactly. And this paper really shows how those two ideas are actually deeply intertwined.
That's cool. So let's maybe unpack those concepts a bit more. First, the isoperimetric profile.
Okay.
How would you define that?
Well, the isoperimetric profile is denoted by the Greek letter phi of n's, and it measures the smallest possible ratio of the boundary size of a set to its volume for all sets of size n.
Okay.
So it essentially quantifies how easily information can leak out of a set on the graph.
So if you have a low isoperimetric profile, that would kind of suggest a leaky graph.
Exactly.
Where information can flow pretty easily across those boundaries.
Precisely.
Okay, cool. Now let's move on to the total variation profile, denoted by TVN.
Yeah, so TVN captures how quickly information spreads on the graph via a lazy, simple random walk. And we look at that by observing two random walks starting at neighboring points and kind of seeing how quickly those paths diverge.
Okay, so a small TVN would indicate that those walks tend to stick together, and therefore information is kind of spreading slowly.
Exactly. And what's really interesting is that the key insight of this paper is that if you have a small TVN that actually implies the existence of sets with these small boundary to volume ratios.
Oh, that's really cool.
And
so if the gossip is spreading slowly, it's hinting at these sort of tightly knit communities.
Yes, that's a great analogy.
Within the network.
And this is what Theorem 1.1 formally establishes. So it states that if the total variation distance TVN between random walks starting at adjacent vertices is small at a given time, then there must be sets on the graph with small boundary to volume ratios.
Wow, so just by observing how slowly information is spreading, you can actually tell something about the underlying structure of the graph.
Exactly. It's like having a new lens to examine the geometry of the graph just by analyzing how information diffuses through it.
That's awesome. Now, to make this a little bit more concrete, the paper goes into some specific examples, right?
Yes.
They look at familiar spaces like Euclidean space, and then they even get it to the more complex lamplighter group.
Yeah. So, for example, in Euclidean space, which is denoted as Z, the theorem yields a bound on the isoperimetric profile that's remarkably close to the actual value. It's only off by a logarithmic factor of log n.
That's pretty impressive.
Yep.
So even in a space like ZD, which is very well understood, this theorem can still provide some valuable insights.
Indeed. And then they move on to the lamplighter group, which is Z2 Reth Z, which is a much more intricate structure. But again, by examining the decay of TVN, the theorem is able to kind of give us new insights into its geometry.
Okay, now before we get too deep into those examples, I'd love to get a better understanding of how they actually prove this connection between TVN and the isoperimetric profile.
Okay.
The proof seems to hinge on this really clever construction involving coupling of random walks.
Right at the heart of the proof lies this idea of a simultaneous near-optimal coupling of random walks. And you can kind of picture it as this carefully choreographed dance where you try to keep these random walks as synchronized as possible. So the goal is to define them on the same probability space in a way that maximizes their chance of staying close together.
So you're kind of like coordinating their movements.
Exactly.
So that they're sort of mirroring each other as much as possible.
Precisely. And to achieve this, they utilize a result by Angel and Spinka, which is stated as Theorem 3.1 in the paper.
Okay.
And this theorem essentially gives you a recipe for constructing this coupling where the probability of the two walks diverging is very tightly controlled by their total variation distance TVN.
Okay, so now we have this carefully synchronized dance of random walks.
Right.
How does this actually help us find sets with small boundary to volume ratios?
Yeah, so this is where the real ingenuity comes in, and it all revolves around lemma 3.3.
Okay.
And this lemma relies on the mass transport principle, and it allows us to analyze the expected boundary to volume ratio of a randomly chosen cell within our coupled walk construction.
Now hold on a second. The mass transport principle.
Yeah.
Can you just remind me how that works again?
Sure. So the mass transport principle is this powerful tool for analyzing global properties of a graph by kind of tracking how mass flows between vertices. It's almost like studying traffic patterns in a city. Right. We're interested in the overall distribution of traffic, so we look at the average movement between different areas.
So in this case, instead of cars, we're tracking the mass of the boundary of these coupled random walk cells.
Exactly. And what's really clever is that lemma 3.3 connects the probability of two walks diverging, which we know is controlled by TVN, thanks to our coupling, to the average boundary to volume ratio of these cells across the entire graph.
Ah, I see. So the smaller our TV, the tighter our coupling, and therefore the smaller those expected boundary to volume ratios.
Precisely. And since we're dealing with amenable graphs, which we know have sets with small boundary to volume ratios, we can combine that with our analysis of the coupled random walk to ultimately prove the existence of these robust sets as outlined in Theorem 1.1.
Wow, that's incredible. So by really cleverly weaving together these concepts of couplings and the mass transport principle and the properties of amenable graphs, they build this powerful link between the spread of information and the graph's inherent geometry.
Right. It's really quite remarkable.
This is all very fascinating, but I'm sure our listeners are eager to see how this theorem is applied to those specific examples that you mentioned earlier.
Yes, I think they'd enjoy that.
But maybe this is a good place to take a quick break. So we'll be back soon to delve into those fascinating examples and uncover the implications of this remarkable theorem for the world of graphs with non-negative Ollivier-Ricci curvature.
Sounds good.
All right, so before we jumped into the break, we were really starting to explore how this paper links the decay of TVN, our total variation profile, to the presence of sets with these small boundary to volume ratios.
And now it's time to delve into the realm of graphs with non-negative Ollivier-Ricci curvature.
Ooh.
This is where this paper really shines.
Ollivier-Ricci curvature on graphs.
Yeah.
That sounds kind of intimidating. Can you give us like a quick refresher?
So imagine you have the concept of Ricci curvature on manifolds.
Okay.
And that kind of tells you how much geodesics, those shortest paths between points,
Right.
tend to either converge or diverge.
Yeah, I vaguely remember that from my differential geometry days.
Yeah.
But how does that apply to graphs?
Well, so graphs don't have these smooth curves like geodesics.
Right.
Instead, what we have are random walks. So Ollivier-Ricci curvature on a graph captures how much two random walks starting at neighboring vertices will tend to converge or diverge, assuming an optimal coupling.
So instead of geodesics, we're kind of looking at the paths of those random walks and analyzing how they spread out across the graph.
Exactly. And just as non-negative Ricci curvature in manifolds places these very strong constraints on the geometry, non-negative Ollivier-Ricci curvature on graphs has these really profound implications.
Wow. Okay, so how does the paper's main theorem, that link between TVN and isoperimetric profiles, help us understand graphs that have this non-negative curvature?
That's where corollary 1.5 comes into play. This result essentially uses the main theorem to give us a quantitative bound on the isoperimetric profile of graphs with non-negative Ollivier-Ricci curvature.
So because we know these graphs have non-negative curvature, which in turn is kind of controlling the random walk behavior, we can use the main theorem to directly get a handle on their isoperimetric profile.
Precisely. It's this chain reaction,
Okay.
non-negative curvature influencing the random walk behavior, which then dictates the graph's isoperimetric properties, all thanks to that main theorem.
That's really cool. So what does this bound actually look like?
So corollary 1.5 states that for a graph G with degrees bounded by M and non-negative Ollivier-Ricci curvature,
Okay.
the isoperimetric profile phi of n is bounded above by a constant multiplied by the square root of m times log of m, all divided by log of n.
Okay, so let me break that down. So a larger degree bound M could lead to a larger isoperimetric profile,
Yeah.
which makes sense because a larger degree bound could allow for kind of leakier sets.
Excellent observation.
And then as n, the size of the set we're considering, increases,
Right.
the bound on the isoperimetric profile actually decreases.
It does.
So that suggests that larger sets in these graphs tend to have smaller boundary to volume ratios, making them more robust to information flow.
Exactly.
This is really painting a nice picture of how that non-negative curvature is really shaping the geometry of these graphs.
Indeed. And what's really remarkable is that this bound is essentially optimal, at least in the high degree regime, as demonstrated by the example of random abelian Cayley graphs.
So we have this amazing result that links curvature to isoperimetry, and it's backed up by examples showing it's kind of as sharp as it can be.
Exactly. It's a beautiful example of how these seemingly abstract concepts from probability and geometry can really come together to reveal these deep insights.
Absolutely.
Yeah.
Now, I have to admit, the paper's journey to get to this result was pretty complex.
Oh, yeah.
There's a lot of intricate mathematical machinery working behind the scenes, particularly when it comes to establishing those upper tail estimates for the random walks displacement and information content.
Right.
You're talking about Theorem 2.1, right?
Exactly.
Can we maybe dive into that a little bit? It seems like a key stepping stone towards the main theorem.
Yeah, definitely. So imagine you're kind of watching this random walk on our graph.
Okay.
Theorem 2.1 essentially tells us that this walk is highly unlikely to stray too far from its expected path, both in terms of distance traveled and the information that it carries.
Now, when you say information, what exactly do you mean in this context?
Right. So in this context, information is captured by the quantity negative log of p sub n of x0 xn,
Okay.
where p sub n of x0 xn represents the probability of the random walk starting at x0 and ending up at xn after n steps.
So a smaller value for p sub n of x0 xn means that the walk is less likely to take that specific path,
Right.
and therefore that path carries more information.
Exactly. You can think of it like sending a message.
Yeah,
A rarer message is more surprising and
Yeah.
thus carries more information.
Gotcha. So Theorem 2.1 is saying that our random walk tends to stick to paths that are relatively likely.
Yes.
Paths that don't carry as much surprise or information.
Exactly.
Okay.
And to prove this, they introduced this really interesting tool called the massive green metric. And this metric measures distances on the graph based on the probability of two walks meeting before a certain time.
So instead of simply counting edges, the massive green metric is taking into account the dynamics of those random walks on the graph.
Precisely. And by applying proposition 2.2
Okay.
to this massive green metric,
Okay.
we gain control over how far a random walk can deviate in terms of information content.
Gotcha.
And this paves the way for the main theorem and all of its powerful applications.
This has been an amazing journey through some pretty deep mathematical concepts.
It has.
And there's still so much more to uncover about the connections between random walks, isoperimetry, and curvature.
Absolutely.
And we're back for the final part of our deep dive into this fascinating paper that connects isoperimetry and total variation decay.
Yeah, it's been quite a journey exploring the world of random walks, isoperimetric profiles, and these graphs with non-negative Ollivier-Ricci curvature.
And we saw how the paper's main theorem, Theorem 1.1, gives us this incredible tool to connect the spread of information on a graph captured by TVN to its underlying geometric structure, revealed through its isoperimetric profile.
We also saw how this theorem, together with those really powerful upper tail estimates for random walks, lead to corollary 1.5, which gives us a remarkably sharp bound on the isoperimetric profile of graphs with non-negative curvature.
Now, before we wrap up, I'd love to circle back to the proof of Theorem 1.1. We kind of glassed over some of the finer points earlier.
Right.
But there were some really ingenious steps in there that I think our listeners would appreciate.
Definitely.
Especially that construction of sets with small boundary to volume ratios that was achieved through that simultaneous near-optimal coupling of random walks.
Right.
Now, we talked about how that coupling based on Theorem 3.1 by Angel and Spinka helps synchronize those random walks and minimize their divergence.
Yeah.
But how do we actually go from these coupled walks to actually pinpointing these special sets?
So that's where Lemma 3.3 comes in, and it involves this beautiful application of the mass transport principle.
Okay, now you mentioned that before, but I have to admit the mass transport principle has always been kind of a mystery to me.
Yeah, it's a surprisingly powerful tool. You can think of it as a way to analyze global properties of a graph by very meticulously accounting for how mass flows between vertices.
Okay.
So in this case, the mass we're interested in is the boundary of those coupled random walk cells.
So instead of analyzing each cell individually, the mass transport principle lets us look at the average boundary to volume ratio across the whole graph.
Exactly. And what Lemma 3.3 does is it uses this principle to connect the probability of two walks diverging, which we know is controlled by TVN, thanks to our coupling, to the average boundary to volume ratio of these cells across the graph.
Ah, I see. So we're using this cleverly constructed coupling.
Right?
And then we're getting that global perspective with the mass transport principle.
Exactly.
And that allows us to prove the existence of at least one cell that has that desired small boundary to volume ratio.
Exactly. It's this really nice interplay between local and global analysis,
Right.
probabilistic and geometric insights.
Yeah, it's really remarkable how this paper brings together so many different mathematical ideas to illuminate this deep connection between information spread and geometric structure.
And the implications extend far beyond just these specific results presented here.
Right.
It really opens up new avenues of research,
Yeah.
particularly in the study of graphs with non-negative curvature.
And speaking of which, the paper hints at this particularly intriguing open question, whether non-negatively curved bounded degree graphs of superpolynomial growth even exist.
That's right. And while the paper doesn't definitively answer this question, it does offer some pretty tantalizing clues. The fact that corollary 1.5 provides such a tight bound on the isoperimetric profile for these graphs suggests that finding examples with superpolynomial growth could be incredibly challenging, maybe even impossible.
It's almost like the paper's throwing down the gauntlet. It's saying, hey, here are these powerful constraints on the geometry of these graphs. Think you can find one that breaks free? Good luck.
It's a call to action for mathematicians to really push the boundaries of our understanding of these intricate relationships between curvature growth and isoperimetry in graphs.
Well, this has been an amazing journey. We've really only scratched the surface of this paper's depth and its implications. But I hope our listeners have gained a new appreciation for the power of random walks,
Yeah,
the elegance of the mass transport principle,
definitely.
and the deep mysteries that still lie hidden within the realm of graph theory.
There's always more to explore.
So to our listeners out there, keep those minds curious, keep those tensils sharpened, and keep exploring the wondrous world of mathematics.
Absolutely.
Until next time, happy deep diving.
Thanks.
Welcome back, everyone. We're diving into some really cool graph theory today.
Yeah, some cutting-edge stuff.
Straight from a 2024 paper by Hutchcroft and Lopez.
This one is all about how a graph's shape, it's isoperimetric profile.
Right.
It connects to how a random walk on that graph, a lazy one to be precise, mixes over time.
The total variation decay, right?
Yeah, exactly.
This is going to be good, especially if you're into those, what they called expanders.
Expanders, yep. And what's really wild is how they tie this to curvature.
Curvature. But graphs are discrete.
That's the thing. They're using Ollivier-Ricci curvature, something usually reserved for continuous spaces.
Okay, hold on. I'm already feeling a little lost.
Yeah.
Can we back up a sec and make sure we're all starting on the same page?
Sure.
So picture a connected graph. We'll call it G. It's locally finite, meaning each vertex has a finite number of neighbors.
Right. And we've got our usual graph distance d sub g sub between any two vertices.
Okay, I'm with you.
Now, we're going to be looking at sets of vertices, specifically their boundaries.
So like the edges connecting those vertices to the outside world.
Yep, that's the boundary, denoted U for a set W. Now, imagine a random walk on this graph, but it's lazy.
Lazy.
Lazy meaning at each step, it either stays put with probability 12 or moves to a random neighbor.
Okay, so it chills out half the time. Makes things smoother, I guess.
Exactly. And we can describe how this lazy walk spreads out after n steps using its transition matrix, sub-sub.
Gotcha. So how do we measure how mixed up this random walk gets on the graph? That's where total variation comes in, right?
You got it. We use the total variation profile, TV sub-sub, which basically tells us how different the distributions of two walks starting at neighboring vertices are after n steps.
Distributions.
Yeah, like where is the walk likely to be after n steps? If those distributions starting from neighboring vertices are similar, that means the walk is mixing well. It doesn't really matter where you started.
Makes sense. But how does all this random walk stuff connect to the shape of the graph itself? Like how well connected it is overall?
That's where the isoperimetric profile steps in. It measures the best ratio of boundary size to the volume of a set, where volume is like the total degree of vertices in the set.
Okay. So small n means there are big sets that are kind of isolated with few connections to the rest of the graph.
You got it. And now, the big reveal, the main theorem of the paper, Theorem 1.1.
Drumroll, please.
This theorem says that if the total variation, TV sub-sub, is small, meaning the random walk mixes well,
Right.
then you're guaranteed to have sets of vertices that aren't too big in terms of both diameter and volume. And importantly, these sets have small boundary to volume ratios.
So good mixing forces the graph to have these well-connected regions. That's wild.
It is. And it's not just a theoretical thing. The proof is constructive. You can actually find these sets using a clever way of coupling random walks.
Coupling.
Yeah, basically you run two random walks in parallel, trying to keep them close together for as long as possible.
Okay, hold on. Let's break down this proof a bit. I'm already feeling a little overwhelmed.
No problem. So to prove this theorem, we use what the authors call a simultaneous near-optimal coupling.
Okay, that's a mouthful. What does that even mean?
So picture two of those lazy random walks, x and y, starting at neighboring vertices. We want to couple their movements. Basically, at each step, we decide how they move together in a way that minimizes the distance between them.
So they kind of stick together as much as possible.
Yeah, but there's a twist. We want this coupling to be near optimal, not just for one step, but for all steps up to some time n. That's the simultaneous part.
So we're trying to keep these walks close together for as long as we can. Why is that important?
The intuition is if the walks stay close together for a long time, it means their distributions are very similar, which means TV sub-sub is small.
Ah, I see. So the coupling is like a bridge between the total variation distance and the actual paths of the random walks themselves. But how do you actually make this coupling work? Like, how do you decide how to move the walks at each step?
It involves a clever recursive procedure. Let's say you already have a coupling for the first k steps. You've decided how the walks moved up to that point.
Right.
To go to k+1 steps, you look at all possible pairs of neighbors, one for each walk.
Okay.
And for each pair, you calculate the Wasserstein distance between the distributions of the walks, starting from those neighbors, but looking ahead to the remaining NK steps.
Wait, so you're looking into the future to decide what to do in the present?
Exactly. You choose the pair of neighbors that minimizes this Wasserstein distance, and then you couple the walks so that they move to those neighbors with the highest probability possible. This keeps the expected distance between them small.
That's pretty clever. But how does this coupling lead to those bounds on diameter, volume, and boundary-to-volume ratio that the theorem promises?
That's where things get really interesting. We need to introduce a stopping time. Think of it like hitting pause on the coupled walks when something specific happens.
Okay, like what?
Well, in this case, we stop when the walks get too far apart, exceeding some threshold that depends on the expected displacement d sub and the total variation tv sub.
So we're watching them closely, and then bam, they cross that line and we hit pause.
Right, and then the magic happens by analyzing what went on before and after that stopping time. But I think that's a good cliffhanger to leave things on.
You're killing me.
Yeah.
But all right, we'll have to wait for part 2 to hear the rest of the story.
It'll be worth the wait, I promise.
All right, so where were we? Yes, we just hit pause on our coupled random walks. They got too far apart, triggered that stopping time.
Right. And now the fun begins. We use the stopping time to bridge the gap between those random walks dancing around on the graph
Right.
and the isoperimetric properties, the shape of the graph itself.
Okay, but how do we do that?
It's all about what happens before and after the stopping time, that pause moment. See, before the walks separate too much, their distributions haven't had a chance to diverge much.
You're still kind of sticking together, distribution-wise?
Exactly. So we can relate the probability of hitting a certain set of vertices, call it W, before the stopping time, to the distribution of just a single walk, starting at either of the initial points.
Okay, I'm following.
Now, after that stopping time, things get interesting. The walks are far apart, right?
Right, that's why we hit pause.
And we can exploit that separation to build a special set, a set with a small boundary to volume ratio.
Hold on, slow down a bit. How do we get that set?
Let's say you've got a set W, just any set of vertices. We want to find a subset of W with a tiny boundary compared to its size. Focus on the vertices in W that are easy to hit before the stopping time. Like, for the walk X, what's the probability of hitting a vertex Z in W before we hit pause?
Okay, so some vertices are more likely to be visited early on.
Exactly. Take all the vertices in W that have at least a 50-50 chance of being hit by X before that stopping time. Call that subset S.
Right, so S is like the easily reachable part of W.
Yep. And because our walks are coupled so cleverly, the probability of the other walk, Y, hitting S before the stopping time is also pretty high.
Why is that?
Because they're sticking close together. If Y was wandering off somewhere else, it wouldn't have time to reach S before things go haywire. So this tells us something important about the edges leaving S.
Let me guess. A lot of those edges have to lead to places near where Y ended up when we hit pause.
Bingo. If many edges from S led to places far away from Y, then Y wouldn't have a good chance of reaching S in time. We've essentially cornered the boundary of S.
I'm seeing it. So the boundary of S is kind of trapped near Y's stopping point.
You got it. And that means we can control the size of the boundary using the volume of a ball around Y's stopping point, the radius of that ball, determined by that threshold distance we used for the stopping time, the one involving the expected displacement d subsets sub.
Okay, that makes sense. So we've got a handle on the boundary. What about the volume of S itself?
Remember the entropy, H sub, it measures how spread out the random walk gets. The higher the entropy, the more vertices are likely to be in that easily reachable set S.
Right, so entropy gives us a way to estimate the volume of S. It's all coming together.
It is, and by carefully juggling these bounds on the boundary and the volume of S, and linking them back to the total variation TV sub, we arrive at the beautiful quantitative estimates in Theorem 1.1.
Wow, that's impressive. They really thought of everything. I'm really struck by how they've mixed probability with the random walks and geometry with the isoperimetric stuff. It's like a perfect blend.
It's elegant, isn't it? A real testament to the power of math. And we're not done yet. This theorem has some pretty cool implications, especially when we bring in Ollivier-Ricci curvature.
Curvature again. But we're talking about graphs, not smooth surfaces.
That's the beauty of it. There's this whole theory of curvature for graphs, and it connects to everything we've been discussing. But maybe we should pause here and save that curvature deep dive for part 3.
You're killing me with these cliffhangers. All right, let's take a break and we'll tackle that curvature mystery next. All right, curvature time. Last we left off, we were teasing this idea of curvature for graphs.
Right. Ollivier-Ricci curvature, to be exact. It's usually something you'd talk about with smooth surfaces like manifolds.
Exactly, like spheres and donuts and such.
But the cool thing is we can define a similar notion for graphs, and it turns out to have some deep connections to the stuff we've been talking about, like isoperimetry and random walks.
I'm intrigued. Remind me, how do we define curvature for graphs again? It's been a while.
So in Riemannian geometry, where you've got those smooth manifolds, Ricci curvature measures how volumes change as you move along geodesics.
Geodesics, those are like the straightest possible paths, right?
Exactly. Now for graphs, we don't have geodesics in the same way, but we do have random walks.
Ah, our trusty lazy random walks.
Yep. And we can use those walks, together with a notion of distance between probability distributions, to define Ollivier-Ricci curvature for graphs. Essentially, we look at how the distributions of two random walks, starting at neighboring vertices, change after one step.
Okay, I'm with you so far. So we're comparing these distributions. How do we measure the distance between them?
We use something called the Wasserstein distance, sometimes called the Earth mover's distance.
Earth mover's distance. That sounds intriguing.
It is. Imagine you have two piles of dirt representing those probability distributions.
Okay, I'm picturing it.
The Wasserstein distance is the minimum amount of work it takes to transform one pile into the other, where work is measured by how much dirt you move and how far you move it.
Ah, I see. So if the distributions are very similar, those dirt piles are already pretty close, and it doesn't take much work to transform one into the other.
Right. So to define Ollivier-Ricci curvature for an edge between two vertices, x and y, we look at the Wasserstein distance between the distributions of lazy random walks starting at x and y after one step.
And if that distance is small, the curvature is high.
Well, not quite. We actually define the curvature as 1 minus the Wasserstein distance.
Ah, that makes sense. So high curvature means the distributions are close together, and low curvature means they're far apart.
Exactly. And if this curvature is non-negative for all edges in the graph, we say the graph has non-negative Ollivier-Ricci curvature. It means, in a sense, that random walks tend to converge rather than spread out too quickly.
It's like the graph has a gentle pull, keeping those random walks from straying too far.
That's a great way to put it. And it turns out that graphs with non-negative Ollivier-Ricci curvature share some interesting properties with those smooth manifolds with non-negative Ricci curvature.
Like what?
Well, one key property in the continuous world is that volume growth is constrained. How quickly the volume of balls grows as their radius increases.
Right, so you can't have things expanding too wildly.
Exactly. And it turns out there are similar, though not identical, constraints on volume growth for graphs with non-negative Ollivier-Ricci curvature.
So they can't be too expansive either.
Right. Now, there's a big open question in this area. Can a bounded degree graph with non-negative Ollivier-Ricci curvature have super polynomial volume growth?
Super polynomial, so like growing faster than any polynomial.
Exactly. We don't know the answer yet. It's one of those mysteries that keeps mathematicians up at night.
I can see why. It would be amazing if such a graph existed, but it also seems counterintuitive, given this idea that non-negative curvature should somehow tame the growth.
It's a real puzzle. Now, while the general question is still open, we do have some partial results. For example, Salas proved back in 2022 that if you have a sparse graph with non-negative Ollivier-Ricci curvature, it can't be an expander.
Expanders. Those are like the ultimate well-connected graphs, right? No matter how you slice them, the boundary is always large compared to the interior.
Precisely. They're superstars in graph theory, with applications all over the place.
So Salet's result says that non-negative Ollivier-Ricci curvature rules out these super expanders. It forces the graph to have some bottlenecks, some regions where the boundary is relatively small.
Exactly. And that's where the connection to Theorem 1.1, the main result from the Hutchcroft and Lopez paper we've been discussing, comes into play. Remember, that theorem connects total variation decay, how quickly a random walk mixes, to the isoperimetric profile, that measure of boundary to volume ratios.
Right. Good mixing implies the existence of well-connected regions, those sets with small boundaries.
And Salas's result says those well-connected regions can't be too extreme if you have non-negative Ollivier-Ricci curvature.
So it all ties together. It's like a beautiful web of connections between random walks, isoperimetry, and curvature.
It is, and the Hutchcroft and Lopez paper takes this connection a step further. They use Theorem 1.1 to actually derive quantitative bounds on the isoperimetric profile for graphs with non-negative Ollivier-Ricci curvature.
So they're not just saying expanders are impossible, they're saying here's how close you can get.
Exactly. And their bounds are quite strong, especially considering they work for any graph, even infinite ones.
That's impressive. It really shows how powerful these abstract mathematical tools can be.
It does, and it leaves us with some tantalizing open questions. Can we find even tighter bounds on the isoperimetric profile, maybe for specific families of graphs? Are there lower bounds connecting total variation decay and isoperimetry?
So much more to explore. This has been a truly mind-bending deep dive. I'm feeling inspired to go read that paper now.
Me too. It's a great example of how seemingly disparate areas of math can come together in unexpected and beautiful ways.
And to our listeners, thank you for joining us on this journey. Keep those mathematical minds curious, and who knows, maybe you'll be the one to crack that open problem about volume growth and non-negative curvature. All right, so today we're going to be diving into some pretty heavy math, looking at isoperimetry and total variation decay in graphs. We're looking at this paper, a relation between isoperimetry and total variation decay with applications to graphs of non-negative Ollivier-Ricci curvature by Tom Hutchcroft and Isaac M. Lopez.
Yeah, this is a really cool paper.
I figured you'd like it.
Yeah.
So it basically shows how the shape of a graph, kind of like the ratio of its boundary to its volume, is actually connected to the way that random walks on that graph will behave and how they spread out. And that connection is really interesting, especially when we start talking about graphs with this property called non-negative Ollivier-Ricci curvature.
Yeah, we can kind of think of that as like a way of measuring how curved the graph is in a sense.
Yeah.
And it actually turns out to have a lot of really interesting implications.
So before we get into the nitty-gritty of their findings, I think it would be helpful to just kind of step back and make sure we're all on the same page with this concept of total variation decay. It's kind of a mouthful. Can you maybe give us a more intuitive way to think about what that actually means?
Yeah, so let's imagine we have two gossip mongers who are starting rumors at different points in a social network. So the total variation distance, that's like a way of measuring the probability that these two rumors, they're spreading kind of like random walks, that they'll end up in different parts of the network.
After a certain number of steps, right?
Exactly, yeah. After a certain amount of time.
Yeah, so it's basically how much does the starting point of that rumor, influence where it ends up?
Exactly, yeah. And the rate at which that total variation distance decreases as the rumors spread further, that's what we call the total variation decay.
Okay.
And it reflects how quickly these rumors kind of mix and become independent of where they originated.
Right.
And actually, this is related to another concept in graphs called the Liouville property, which is kind of a similar idea.
Liouville property. Yeah, that rings a bell, but I'm a little fuzzy on it. Could you maybe give us a quick refresher on that?
Yeah, so you can think of it this way. Imagine a heat map on our social network. So, if the heat from these rumors can spread out evenly and it can't, get concentrated in any particular hot spots, that's kind of like the Liouville property in action.
Oh, okay. So it's kind of like the network has no heat traps.
Exactly, yeah.
All right. So how does all of this tie back into this paper that we're looking at?
Well, the main result of this paper, which is Theorem 1.1, actually directly relates this, total variation decay to the graph's isoperimetric profile, which, as you said earlier, kind of quantifies the shape of the graph.
Okay, so Theorem 1.1 sounds like it's kind of the key here. But before we get too lost in the, the mathematical weeds, can you just kind of walk us through what this theorem actually says? If you were explaining it to a colleague over coffee or something?
Yeah, sure. So basically it says that if the total variation distance between random walks starting at neighboring points, if that decreases really rapidly, then it means the graph has to have some regions where the, ratio of the boundary to the volume is small.
Oh, okay.
So it's kind of like saying that if rumors can mix very quickly, then the network can't be too spread out. It has to have these densely connected pockets where information flows really easily.
So if random walks quickly forget where they started, basically, the graph can't be too blanchy or have all these bottlenecks. It has to have those densely connected pockets.
Exactly, yeah. And actually the theorem goes even a little further, and it suggests that we can actually, kind of refine those size constraints on these regions. If we actually know a bit more about the random walks, how far do we expect them to travel? Or, how much do their paths kind of branch out, which we can measure using this idea of entropy.
Interesting. So the more we know about those gossip mongers and the way they like to spread those rumors, the more we can actually pinpoint exactly how the network itself is structured. Now, there's this remark 1.2 that I found pretty interesting. It talks about simultaneous near-optimal coupling. Can you maybe unpack that for us a little bit?
Yeah, so I like to think of it kind of like we're choreographing our gossip mongers. Instead of just letting them spread their rumors randomly, we're kind of like subtly influencing them so that they stay close together as they move throughout the network.
So we're nudging them to spread those rumors in a more synchronized way.
Exactly. Yeah. And, this coupling, it turns out, is really crucial for proving that main theorem. And the authors actually use it to partition the network into these, regions that actually have this, desired property of having small boundary to volume ratios.
So it's like we're using these, coordinated gossip mongers to actually map out the network's natural clusters.
Exactly, yeah. And this leads us very nicely to corollary 1.3, which brings in this idea of how quickly the random walk kind of, spreads out or explores, which is captured by entropy.
Right.
And how that affects the isoperimetric profile.
Okay, so corollary 1.3 basically gives us a way to estimate the isoperimetric profile if we know how quickly the entropy is growing for the random walk and how quickly the total variation is decaying.
Exactly, yeah. So it's letting us kind of quantify how the network's shape constrains how, far and wide those rumors can actually spread.
Okay, I see. So it's like if we know how quickly a rumor picks up steam, how fast it's growing, and how easily it can blend into the network, that can tell us a lot about the underlying structure of the network itself.
Yeah, exactly.
And they use some interesting examples to illustrate this, right?
Yeah, so they actually use the, very familiar grid-like graph, which is kind of denoted by ZID. And they also use something called the lamplighter group, which is a bit more of a kind of a strange example, but it's useful for seeing how this corollary can work in, less intuitive situations.
Yeah, the lamplighter group.
Yeah.
I always love these names that mathematicians come up with. Can you maybe give us a little bit of a sense of what, why they call it that, or, what is the lamplighter group?
Yeah, so you can think of it as like a person walking along this line of lamps and randomly toggling them on or off.
Okay.
So it's, it's obviously a little bit more abstract than just like the standard grid, but it's useful for seeing that, these tools can apply to a wide range of settings.
Yeah, it's like, hey, look, this stuff isn't just theoretical. This can work even in these, bizarre lamplit mathematical worlds. Now, before we go too much further down that road, I think it's worth just kind of taking a step back and looking at the bigger picture for a second. Are there other, connections that we know about between these concepts? Total variation, entropy, isoperimetry, like what else is out there that mathematicians have kind of uncovered in this realm?
Yeah, for sure. I mean, this whole area is full of these really fascinating connections. For example, there's this thing called the Vertices-Carnot inequality,
Okay.
which relates the expected displacement of a random walk, like how far we expect it to travel, to its entropy.
Okay.
So it's kind of saying that, the further that a rumor spreads, the more kind of unpredictable its path becomes.
Interesting.
And then there's also, this idea of the spectral profile, which is a tool that captures a lot of information about the eigenvalues of a graph's Laplacian, which turns out to be related to both isoperimetry and random walk behavior.
So it's like this hidden code inside the network that influences both its shape and how things move around on it.
Yeah, exactly.
What else is there?
And then there's also something called the return probability, which is, what's the chance that a random walk will actually come back to its starting point eventually?
Okay.
And this turns out to be closely linked to the, the network structure and also entropy as well. So, it's kind of like asking, what are the chances our gossip monger is going to accidentally stumble back on the source of their original rumor?
Interesting. So it's kind of remarkable how all these things are connected, right? Like the shape of the network, the spread of rumors, the chance of retracing your steps. It's all kind of, woven together in this intricate way.
Yeah, absolutely.
So now I think we're ready to move on to section 1.1, where the authors really start to dig into how all of these ideas apply to those graphs with non-negative Ollivier-Ricci curvature. The ones where those random walks tend to kind of cluster together.
Yeah.
Let's get back to those gravitational networks. I think that's a really interesting test case for all these concepts.
Yeah, for sure. And they actually provide like a really intuitive explanation of what Ollivier-Ricci curvature is, drawing these parallels to like Ricci curvature in Riemannian geometry. And the key idea is just thinking about, how do random walks on a graph tend to spread out or coalesce? Just like, how geodesics behave in curved spaces.
So in those graphs with non-negative Ollivier-Ricci curvature, it's basically saying that those rumors, they tend to, clump together rather than spread out. Like there's kind of this gravitational force pulling them in.
Exactly, yeah. And, having this non-negative curvature actually leads to some pretty interesting consequences.
Okay.
One of which is that it limits how spread out these graphs can actually be, even though, they're random walks like to stick together.
Okay, so there's kind of a limit on how tightly clustered those networks can get. It's like there's some counterforce that keeps them from just totally collapsing in on themselves.
Yeah, exactly, yeah. And this is where corollary 1.5 comes into play, which actually gives us like a very specific upper bound on how spread out these, special graphs can be.
Corollary 1.5.
Yeah.
All right, this sounds like a pretty important insight. Can you unpack that a little bit for us?
Yeah, so basically what it says is, even though, random walks on these graphs tend to coalesce, to come together, there's a limit on how tightly they can cluster. So it gives us this concrete mathematical bound on this clustering that quantifies how the curvature of the graph is kind of restricting its shape.
So even with this, gravitational pull drawing things together, there's still some amount of, expansion that has to happen.
Yeah.
It can't just become completely insular.
Exactly. Yeah. And what's really interesting is that this corollary actually strengthens a previous result that was, proved by Munch and Salez.
Okay.
And it extends it to cover both infinite graphs and a wider range of, scales within the graph. So it's a more powerful tool for understanding how these ideas, play out.
So it's like they took this existing idea and they made it even sharper so they could see even more of the fine details.
Exactly, yeah.
All right, well, I think this is a great place to pause for now. We've covered a lot of ground, kind of set the stage for really digging into the details.
Yeah, I think so.
And next time we're going to really dive into the proof of Theorem 1.1 and how they actually construct those regions, those tightly knit regions with small boundary to volume ratios.
Yeah, it's a really cool construction, and I think, it'll give us a much deeper understanding of how these ideas actually work in practice.
Sounds good. Looking forward to it.
Yeah, me too. Welcome back. So let's get into the proof of Theorem 1.1 and see how those sets with these small boundary to volume ratios, how they're actually constructed. And the key to this really lies in section 2 of the paper, where they demonstrate that the random walk, its displacement and the information associated with it, they rarely exceed their expected values by a significant factor. So they're basically showing that random walks, they kind of tend to stick to this predictable path.
Okay, so they're not like going on these crazy tangents, these random walks are gossip mongers.
Yeah, exactly. And Theorem 2.1 really formalizes this by giving us these exponential tail bounds for both the displacement, so, how far the walk travels, and the information, which is kind of like a measure of, how much surprise or uncertainty is associated with the path of the walk.
So like if a rumor usually spreads to, 10 people in a day, it's really unlikely that it's suddenly going to jump to like 100 people.
Yeah, that's a good way to think about it. Yeah, these bounds are basically telling us that like those really extreme deviations from the expected behavior are really rare.
That makes sense intuitively, but how do they actually prove these bounds?
Yeah.
Like it seems kind of tricky to, mathematically pin that down.
Yeah, it is. And they use this clever combination of like concentration inequalities and a deep understanding of how the graph structure kind of influences the behavior of the random walk. And interestingly, they actually start by proving this more general statement, which is proposition 2.2, which provides these tail bounds for like any metric that we define on the graph, not just the, standard graph distance.
Okay, so instead of just looking at, how many steps it takes to get from A to B, they're like, well, let's consider any way of measuring distance or closeness between points on the graph.
Yeah, exactly. And this generalization is really powerful because it lets them apply their results to like a much wider range of scenarios. Now, the proof of proposition 2.2 is it's pretty intricate. It involves like carefully analyzing these things called stopping times and a clever use of Markov's inequality. It
sounds like some serious mathematical firepower.
Yeah. Definitely. But the payoff is worth it because once they have proposition 2.2, they can apply it to these specific metrics like the, standard graph distance and this thing called the massive green metric to get the tail bounds they want for displacement and information.
Ah, yes, the massive green metric. We touched on that a bit earlier. Can you just remind us, what is that and how does it fit into all of this?
Yeah, so imagine you're traveling between cities and your notion of closeness is based on how easy it is to get from one city to another.
Okay.
So cities with lots of direct flights would be considered closer than ones where you have to take multiple layovers or a really long journey.
Right.
And the massive green metric is kind of similar. It measures distance based on the probabilities of a random walk hitting certain points before a given time.
Okay, so points that are more likely to be visited by a random walk are considered closer under this metric. It's like those cities with the easy flight connections.
Exactly. And this dynamic perspective where you're incorporating the movement of random walks is really key to understanding this relationship between random walk information and the structure of the graph.
Okay.
And so the authors, they use this connection along with this other result, lemma 2.6, which relates this massive green metric to the random walk information. And they use that to prove the information tail-bound in Theorem 2.1.
Okay.
So it's this really nice example of how these seemingly unrelated concepts, can actually be tied together in a very elegant way.
They found this secret bridge between the movement of the random walks and the actual static map of the network.
But let's get back to the construction of those sets with those small boundary to volume ratios. How do these tail bounds actually help us with that? Yeah, so these tail bounds are kind of like the building blocks. They're telling us that with high probability, a random walk, our gossip monger, they're going to stay within a certain ball around their starting point, both in terms of graph distance and information.
Okay, so they're using these balls of probable movement as the starting point for creating the sets.
Exactly. But instead of just using one random walk, they use this really clever technique called simultaneous near optimal coupling, which we talked about earlier.
Right.
And this allows them to couple multiple random walks, each starting from a different point, so that they all tend to stay close together as they move.
Right. So it's we're kind of, subtly choreographing all those gossip mongers so that they're spreading those rumors in this synchronized way.
Exactly. Yeah. And this kind of coordinated exploration really helps to kind of partition the graph into these regions, where each region consists of all the points whose random walks kind of end up at the same final destination. And because the random walks are all coupled to stay close together, these regions, they tend to have small diameters and small volumes.
So it's they're using these coupled random walks to create these clusters of points that are both geographically and informationally close.
Yeah, that's a great way to put it. And because of those tail bounds we talked about earlier, they can actually control the size of these clusters and make sure they don't get too big. And then the final piece of the puzzle is to show that, okay, at least one of these clusters that we've created, it actually has to have this small boundary to volume ratio.
And that's where lemma 3.3 comes in, right?
Exactly, yeah. Lemma 3.3 is the linchpin that connects this whole Cupson construction to the actual isoperimetric properties of the graph.
Okay.
And basically what it says is that, okay, if you just pick a random point from some finite subset of the graph, the expected boundary to volume ratio of its cluster, that's bounded by the total variation distance between the coupled random walks.
So the more closely those coupled random walks are sticking together, the smaller the expected boundary to volume ratio is going to be for those resulting clusters.
Exactly, yeah. And remember, that total variation distance, we can make that arbitrarily small by just letting the random walks run for long enough.
Right.
So what lemma 3.3 is really telling us is that, okay, somewhere out there, there has to be at least one of these clusters that has this nice small boundary to volume ratio that we're looking for.
So they've taken this this dynamic idea of the random walks and they've translated it into this static property of the shape of the graph.
Yeah, exactly. And it's a really powerful demonstration of how these probabilistic methods can be used to prove, very deep and often unexpected things about, geometry and graph theory.
Mm-hmm.
And it lays the groundwork for understanding how these ideas apply to, these gravitational graphs with non-negative Ollivier-Ricci curvature.
Right, which is what we're going to get to next time.
Exactly.
All right, so we've really spent some time digging into the machinery behind Theorem 1.1 and its proof. And I think now we're ready to kind of bring it back to those graphs with non-negative Ollivier-Ricci curvature, the ones where the random walks kind of, clustered together like they're drawn in by gravity.
Yeah, for sure. I think now we can really see how all this machinery helps us understand how those special graphs are actually structured.
Yeah, and I'm particularly intrigued by corollary 1.5, which you mentioned kind of gives us this like concrete limit on how spread out those graphs can actually be,
Yeah.
even though they have this tendency towards, clustering. Can you maybe say a little bit more about like what that bound actually looks like and what it tells us about the shape of these graphs?
Yeah, definitely. So corollary 1.5 tells us that for a graph with non-negative Ollivier-Ricci curvature and bounded degree, its isoperimetric profile, which we denote by M, that's actually bounded above by this function that grows incredibly slowly with n. So specifically, it's on the order of, square root of m log m divided by log n, where m is like the maximum degree of the graph.
Okay, I'm seeing the math there, but can you maybe translate that into like, what does that actually mean for the shape of the graph?
Yeah, so think of it this way. Even though these graphs have this, natural tendency to kind of form clusters because the random walks on them, like to coalesce, they like to come together, they can't get like arbitrarily tightly packed. There's this fundamental limit on how small the boundary of a set can be compared to its volume.
So even with that gravitational pull, they can't just completely collapse inwards.
Exactly, yeah. That curvature that's captured by that non-negative Ollivier-Ricci condition, it really puts a constraint on how tightly the graph can be packed. What makes corollary 1.5 so powerful is that this bound, it holds for like sets of all sizes within the graph. It's not just for really large sets or, sets of a specific volume or something. So it's giving us this like multi-scale understanding of the isoperimetry.
Yeah, you mentioned earlier that this corollary actually strengthens a previous result.
Yeah.
By Munch and Salez, I believe. Can you remind us like what was their result and how does this new corollary kind of improve upon it?
Yeah, so Munch and Salez, their result also focused on this isoperimetric profile of these graphs with non-negative Ollivier-Ricci curvature. And they also found an upper bound that's similar to the one in corollary 1.5. But theirs only applied to finite graphs and only at a specific scale. So basically for sets whose volume was like roughly half the total volume of the graph.
Yep.
So it was kind of saying that, these graphs can't be what are called expanders, meaning they can't have like a large Cheeger constant, which is like a measure of how well connected the graph is.
So their result was more about like the overall expansiveness of the graph,
Yeah.
whereas corollary 1.5 is giving us like a much more, fine-grained picture of the isoperimetry across all these different scales.
Exactly, yeah. So corollary 1.5, it generalizes their finding in two really key ways. First, it applies to both finite and infinite graphs. And second, it provides a bound that holds for, sets of any size. So it's a much, much more powerful tool for really understanding this interplay between curvature and isoperimetry.
It's really pretty amazing how we started with this, seemingly very abstract notion of total variation decay. And we ended up with this like very concrete and quantitative understanding of the shape of these, pretty special graphs.
Yeah, and I think it's a really beautiful illustration of, the power of mathematical abstraction to reveal these really deep and often unexpected connections between these seemingly like completely disparate concepts.
Absolutely. And before we wrap things up, I just want to circle back to section 2 of the paper real quick, where they really dive into those upper tail estimates for the random walk displacement and the information. We kind of glossed over it earlier, but I think it's worth, highlighting one more time just how important that section really is.
Yeah, definitely. I mean, section 2, that's really laying the foundation for everything that follows. And Theorem 2.1, which is kind of the heart of that section, it's establishing these crucial exponential tail bounds, both for the displacement of the random walk, which is denoted by dg x0 xn, and its information content, which is represented by b slog p n8 x0 xam.
Right. So it's basically, putting some numbers on just how predictable those random walks on these graphs actually are, showing that they tend to stay, relatively close to that expected path, both in terms of where they go and like the information they carry with them.
Exactly. Yeah. And these bounds aren't just, theoretical curiosities. They're really the linchpins that allow the authors to actually do that construction of those tightly knit regions with the small boundary to volume ratios.
Yeah. So those, kind of technical results about tail bounds, they actually have these really profound implications for the overall geometry of the graph.
Exactly. Yeah. And it really underscores, just this very deep and often very subtle interplay between the dynamics of random walks and the static properties of the underlying structure of the graph.
Well, I think we've covered an incredible amount in this deep dive. We've explored this fascinating connection between isoperimetry and total variation decay. We unpacked this, very elegant construction of those sets with those small boundary to volume ratios.
Yeah.
And we saw how all of this comes together to really help us understand the structure of these graphs with non-negative Ollivier-Ricci curvature.
Yeah, it's been a really, fun and captivating journey through this very rich mathematical landscape. And I think it really showcases the beauty, the power, and just the interconnectedness of all of these concepts.
Absolutely. And before we sign off, I want to leave our listeners with one final thought. We've been talking about these abstract graphs here, but could these, mathematical tools be applied to, more real-world networks, like social networks or the internet? Could they help us uncover hidden patterns and structures in these, very complex systems, where understanding how information flows and how these clusters form is so crucial? It's a question we're thinking about as we wrap up our deep dive into this fascinating world of isoperimetry and random walks. Thanks for joining us.
Thanks for having me. It's been fun.
Welcome back, everyone. We're diving into a paper today that connects two things in graph theory you might not think go together at first.
Yeah, it's really quite surprising.
Isoperimetry and the way the decay of random walk total variation. It's
really interesting stuff.
it's a fascinating paper,
Yeah.
even for those of us who
Absolutely.
work with graphs all the time.
Oh, yeah. Big time.
So are you ready to unpack this?
I am very much so.
All right.
Yeah, let's do it.
The paper is titled A Relation Between Isoperimetry and Total Variation Decay with Applications to Graphs of Non-Negative Ollivier-Ricci Curvature. It was published just this month by
Very recent.
Tom Hutchcroft and Isaac M. Lopez.
Nice.
Now, we're not going to shy away from the complexity here,
No?
but we are going to try to make it digestible and memorable.
Yes. And the core insight, I think, is surprisingly intuitive once we break it down.
Okay, good.
Yeah.
So let's start with the central result,
Right.
Theorem 1.1.
Okay.
Now, this theorem basically says that if you can show that random walks starting from neighboring points on a graph become statistically similar quickly,
Right.
then your graph has to have sets with a low boundary to volume ratio.
Yeah.
It's almost like,
It's a very interesting connection between these two seemingly disparate concepts.
yeah, so good mixing of those random walks implies some interesting geometric properties.
Absolutely. And you could almost think about it like the spread of gossip in a network
Okay.
dictates something about the shape of the network itself.
I like that analogy.
Yeah.
So to make this more concrete,
Okay.
can we kind of unpack those key quantities that the theorem uses?
Absolutely. So first we have the total variation profile,
Okay.
which is denoted by TVN.
Mm-hmm.
And this measures how different the distributions of two random walks,
Okay.
starting at neighboring points or after n steps.
Okay.
So going back to the gossip analogy, a low TVN means that the rumors become indistinguishable quickly.
Okay, so fast spreading gossip equals low TVN.
Exactly.
Got it.
Yeah.
What about isoperimetric profile?
So the isoperimetric profile is denoted by this Greek letter phi of n,
Okay.
and it captures how small the boundary of a set
Okay.
within the graph can be compared to its overall size.
Okay.
So good isoperimetric profile means you can have very large sets with relatively small boundaries. So think about like a sprawling country with a surprisingly short border.
Okay, interesting. So Theorem 1.1
Yeah.
is saying that quick gossip mixing
Right.
implies that those kinds of efficient shapes must exist in the graph.
Exactly. Exactly. That's what it's saying.
Wow.
Yeah. And then the paper also introduces these quantities D star n and H star n,
Okay.
which are measures of how far and how spread out a random walk typically gets after n steps. And these quantities are helpful for just kind of understanding how the random walks are behaving.
Okay.
Yeah.
So let's anchor this with an example. Consider the integer lattice Zin,
Yes.
which is, our familiar grid and duting dimensions.
Right.
Intuitively, it seems to have good isoperimetry, right?
Yeah, absolutely.
A large cube within the lattice has a lot of volume.
Yeah.
compared to its surface area.
Right, and that's exactly what the theorem is telling us.
Okay.
The good isoperimetry in ZID is a consequence of the way that random walks behave on the lattice, the way they efficiently explore and mix on this structure.
So the theorem isn't just about observing a connection.
Right.
It's providing a tool.
It's a tool.
To actually find these sets.
Exactly. So if we understand how random walks behave on a graph, particularly if we can control that total variation profile, then we can leverage the theorem to construct sets with those low boundary to volume ratios.
That's powerful.
It's a powerful tool.
Okay, but going back to Zin.
Yeah.
Does the theorem give us the best possible bounds?
That's a good question.
On its isoperimetric profile?
So that's where example 1.4, it's interesting.
Okay.
The authors showed that for simple graphs like ZID, the bounds that you get from the theorem are actually quite close to optimal.
Wow.
However, for more complex graphs, like what's called the lamplighter group, the estimates become less precise.
Interesting. Why is the lamplighter group considered more complex than ZID?
Well, so imagine you have an infinite line of street lamps, each of which can be either on or off. And you have a lamplighter who's walking along this line and toggling the lamps on or off according to some rule. This action can be represented mathematically as a group, and this group is called the lamplighter group.
Okay, but why is it harder?
So the lamplighter's position, combined with the state of each lamp, creates a much larger state space than ZID. So essentially we have this extra layer of information to track, which complicates the analysis of how random walks behave.
So the effectiveness of Theorem 1.1's bounds depends on
the graph.
On the graph's structure.
Exactly. And it highlights the sort of nuanced nature of these inequalities. The theorem provides this fundamental connection. But the precision of its estimates really hinges on the complexity of the graph. So it really reinforces the importance of understanding the specific characteristics of each graph when we're working with it to get the most accurate results.
All right. So far, so good. We've got this amazing connection between total variation decay and isoperimetry. We've seen how it plays out in different types of graphs. But there's one more piece of this puzzle that we need to explore.
Absolutely.
Ollivier-Ricci curvature. Where does that fit into all of this?
So that's where things get really exciting. Ollivier-Ricci curvature is this concept borrowed from Riemannian geometry, which is the study of curved surfaces like spheres and hyperbolic spaces. And it essentially measures how space is distorted around a point.
Okay, but how do we apply that to a graph which is made up of discrete points and edges?
Yeah, that's a great question.
Like, it doesn't seem like we have the same kind of smooth curvature to work with.
So that's the ingenuity of Ollivier-Ricci curvature on graphs. It captures how random walks behave near each other. So imagine you have two random walks that are starting at neighboring vertices. If the curvature is positive, they tend to drift apart as they wander. And if it's negative, they tend to converge.
That reminds me of something.
Think
of blowing up a balloon. On the balloon's surface, the curvature is positive. And as it inflates, those points spread apart. But on a flat piece of paper, the curvature is 0. And nearby points stay roughly the same distance apart.
That's a perfect analogy. So this paper provides a way to study these curvature-like properties on graphs using random walks as our tool. And it turns out that graphs with non-negative Ollivier-Ricci curvature exhibit some really fascinating characteristics.
Like what? Tell me more.
So corollary 1.5 states that if a graph has non-negative Ollivier-Ricci curvature and bounded degrees, then its isoperimetric profile can't be too good.
What does that mean?
So it's limited by a logarithmic function of the set size.
So even though these graphs can have large sets, their boundaries can't be arbitrarily small.
Exactly.
So it's like there's a limit to how efficiently they can pack things in.
Exactly. And if we go back to the balloon analogy, it's like saying that even though the balloon is expanding, there's a limit to how quickly those nearby points can spread apart. So we've come full circle. We began with this seemingly abstract connection between random walks and isoperimetry. Right.
And now we've linked it to this geometric notion of curvature.
Yeah. It's really neat.
It's like we've uncovered a hidden language
I like that.
that connects these different areas of mathematics.
Absolutely. And this connection isn't just some mathematical curiosity.
Oh.
It has real implications.
Okay.
So this result about non-negative curvature actually builds upon previous work by Salez and Munch-Salez
Right.
and extends their findings to a broader range of graphs and scales.
Okay.
So it's a significant step forward
Right.
in our understanding of the interplay between random walks geometry and isoperimetry.
This is incredible, and we haven't even touched on the proof yet.
I know, right?
I'm already feeling my brain stretching in new ways.
Yeah, me too. The proof itself is really where the magic lies.
Okay.
It's just a brilliant display of mathematical ingenuity.
All right. Are you ready to dive into the details?
Well, let's do it.
Lead the way.
Okay. Okay, so Section 2 is all about establishing some
Okay.
crucial upper tail estimates
Okay.
for the random walk's displacement
Okay.
and the information associated with its path.
Mm-hmm.
And these estimates are really like the bedrock upon which the entire proof is built.
Okay. I'm intrigued, but I have to admit the phrase upper tail estimates makes me feel like I'm back in stats class.
I know.
Can you give us a more intuitive sense of what we're trying to control here?
Yeah, absolutely. So imagine you're tracking a random walk
Okay.
as it meanders around the graph.
Mm-hmm.
We want to understand how likely it is for the walk to stray really far from its starting point or to take a path that's extremely unlikely. These upper tail estimates tell us that those extreme events become exponentially less probable as the extremeness increases.
So it's like saying that a really wild, unpredictable random walk is possible,
Yeah,
but highly improbable.
exactly. And the authors capture this formally in Theorem 2.1.
Okay.
So for a graph with bounded degrees, both the displacement,
Okay.
which is how far the walk travels,
Right.
and the information associated with its path,
Okay.
which is like how surprising that particular path is,
Right.
are unlikely to exceed certain bounds.
Okay. I'm starting to get the picture, but how do they actually prove those bounds?
Right.
What's the mathematical machinery involved?
So it's a multi-step process,
Okay.
and it all begins with this rather general statement about metrics on a graph,
Okay.
which is presented in Proposition 2.2.
Okay.
And this proposition is like the engine that drives the proof of Theorem 2.1.
Metrics on a graph, remind me what those are again.
Sure. So a metric is simply a way to measure distance between vertices.
Okay.
So for example, the standard graph distance is a metric.
Okay.
It counts the number of edges in the shortest path
Okay.
between two vertices.
Okay.
But we can define other metrics as well, depending on the context.
Right. That makes sense. So what does this proposition 2.2
Yeah.
tell us about metrics?
So it says that for any metric defined on the vertices of our graph,
Okay.
the maximum distance a random walk travels in steps is unlikely to be much larger than the expected maximum distance.
Okay, that sounds reasonable enough.
Yeah.
Random walks tend to stay within a certain predictable range.
Right, exactly. But Proposition 2.2 goes further and gives us a precise bound. Okay.
On the probability of exceeding that expected distance.
Okay.
And this probability decays exponentially as we move further and further away from the expected value.
So the more a random walk deviates from the norm,
Yeah.
the less likely it is to happen.
Exactly. It's like those bell curves we see everywhere. The tails get thinner and thinner the further you get from the center.
Exactly.
And this exponential decay is key.
Okay.
It allows us to really control the probability of those extreme events.
So how do we go from this general statement about metrics
Yeah.
to the specific bounds in Theorem 2.1 for the displacement and information?
Okay, so for the displacement, it's fairly straightforward.
Right.
We just use the standard graph distance as our metric d, and proposition 2.2 gives us the bound we need.
Okay, that's one down. What about the bound on the information associated with the random walk path?
Right.
It seems a little trickier.
It is a bit more subtle, but equally elegant.
So recall that the information of a path is essentially the negative logarithm of its probability.
Okay.
So the less likely a path is, the more information it carries.
Right. I remember it's like a rare event contains more surprise than a common one.
Exactly. To prove the bound on this information,
Okay.
the authors introduce a special metric called the massive green metric.
Massive green metric. Sounds intriguing. What is that exactly?
It's another way to measure distance on the graph,
Okay.
but instead of simply counting edges,
Okay.
it incorporates the probabilities of the random walk transitioning between those vertices within a certain time frame.
So it's not just about how many steps it takes to get from point A to point B.
Great.
It's also about how likely the random walk is to actually take that path
Exact, sir.
within a given number of steps.
Precisely. The massive green metric gives us this more nuanced view of distance,
Okay.
taking into account both the path length
Okay.
and the likelihood of that path being traversed by the random walk.
I'm starting to see why they call it massive. It seems to pack in a lot of information.
It does. But how does this help us bound the information content of a random walk path?
Right.
So the key insight is to apply Proposition 2.2 to this massive green metric.
Mm-hmm.
By doing so, we get a bound on the maximum massive green distance a random walk is likely to travel.
Okay.
Then the authors very cleverly relate this bound back to the standard random walk information, and voila, we have our desired exponential tail bound on the information.
Okay, I'm going to need a moment to process that.
So-
It's a pretty dense argument.
It is.
But the takeaway is that we now have these tight bounds on how far
Yeah.
and how spread out a random walk is likely to get.
Exactly. We've tamed those unruly random walks,
Okay.
at least in a probabilistic sense.
So now that we've established these bounds, how do they feed into the main result, the construction of those special sets with small boundary to volume ratios?
Right.
That's the ultimate goal, right?
Absolutely. And that's where Section 3 comes in, where the authors introduce their very ingenious simultaneous near-optimal coupling technique.
Okay.
Are you ready for the next stage of this mathematical adventure?
Lead the way, I'm all ears. All right, my brain is primed and ready. Hit me with this simultaneous near-optimal coupling technique. What in the world does that even mean?
That's a really brilliant strategy.
Okay.
The idea is to create a kind of choreography
Okay.
for multiple random walks happening at the same time.
Mm-hmm.
They're not moving in lockstep,
Okay.
but they're subtly influencing each other
That's
in a
right.
way that reveals these special sets we're after.
Okay, I'm picturing a troupe of random walkers doing a synchronized dance routine. But how does that help us find sets with small boundary to volume ratios?
So let's break it down step by step.
Okay.
First, they tame the wildness of the random walks by conditioning them to stay within certain bounds.
Okay.
Remember those upper tail estimates we worked so hard to establish?
Right.
Those come into play here, ensuring that the walks don't wander too far or take paths that are too improbable.
So we're essentially restricting the dancers to a specific part of the stage,
Right.
making sure they don't go rogue and do their own thing.
Exactly. And once we have these well-behaved, conditioned random walks,
Okay.
the authors use a powerful result by Angel and Spinka
Mm-hmm.
to create a coupling between them.
Okay.
This coupling is like the choreography.
Oh, yeah.
It dictates how the random walks move in relation to each other.
So it's not just about each walk individually. It's about how they move together as an ensemble. I'm starting to see the simultaneous part of this technique.
Precisely. And the brilliance of this coupling is that it's near optimal.
Okay.
This means that if two random walks start at neighboring vertices, they are highly likely to stay close to each other under this choreography.
So the coupling keeps those nearby walks from diverging too wildly.
Exactly.
But how do we get from dancing random walks to those special sets?
So here's the ingenious part. The authors use this coupling to define a random equivalence relation on the vertices of the graph. Basically, if two random walks under this coupling end up at the same point after insteps, we say their starting vertices belong to the same equivalence class.
So we're grouping together vertices based on where their coupled random walks end up. It's like saying all the dancers who finish in a certain spot on the stage belong to the same group, regardless of where they started.
That's a great way to put it. And these equivalence classes, let's call them cells,
Okay.
become the building blocks of those special sets we're looking for. Remember, we condition those random walks to stay within those good bounds, so we know that the diameter of each cell, the maximum distance between any 2 points within it,
Right.
can't be too large.
Right, because the dancers weren't allowed to stray too far from their starting position.
Exactly.
But how do we know these cells have those coveted small boundary to volume ratios? That's the whole point, right?
It's subtle but brilliant. The authors introduce a key lemma 3.3, which is based on what's called the mass transport principle. This lemma allows us to relate the average boundary to volume ratio of these cells to the probability that two coupled random walks starting at neighboring vertices will diverge, that is, end up in different cells.
So it's linking the local behavior of the random walks, whether those dance partners split up or stay together, to the global property of boundary to volume ratios of the entire cell.
Exactly. And since our near-optimal coupling ensures that the probability of two neighboring walks diverging is small, it's controlled by that TVN term.
Right.
We can deduce that the average boundary to volume ratio of the cells must also be small.
Wow. So by cleverly controlling the behavior of the random walks with this coupling, and then grouping vertices based on where their coupled walks end up,
Yeah.
we can construct these special sets with the properties we want.
Exactly.
It's like using a choreographed dance to reveal the hidden structure of the stage itself.
It's a beautiful blend of probability graph theory and even a touch of geometry. And it opens up this whole new way of thinking about the structure of graphs, particularly those with non-negative Ollivier-Ricci curvature.
This whole paper has been a revelation. We started with this seemingly abstract connection between random walk mixing and isoperimetry, and now we've seen how it ties into this geometric notion of curvature, and we've even explored the intricate proof that makes it all work. It's like we've gone on a mathematical journey through a hidden landscape guided by these random walkers.
And like any good journey, it leaves us with more questions than answers.
That's right.
Can we refine these inequalities for specific families of graphs beyond those with non-negative curvature? Can we use these insights to design algorithms that efficiently find these special sets in practical applications? There's so much more to explore.
I'm already excited to see where this research leads. A huge thanks to our listeners for joining us on this deep dive into the fascinating world of graph theory, random walks, and the unexpected connections that lie within. Until next time, keep those mathematical minds curious and those explorations ongoing.